Hi, my name is Marina Christakos, and I'm presenting on behalf of my undergraduate team at Worcester Polytechnic Institute to design a novel 3D model for heart valve calcification. Calcific aortic valve disease is where calcium deposits form on the aortic valve and cause the opening of the valve to narrow. This ranges from a mild variation called aortic sclerosis to a more serious disease called aortic stenosis. It's one of the most common valvular heart diseases in the world, with 2 to 4% of individuals over the age of 65 affected by it. After diagnosis, there's an 80% chance of heart failure, death, or valve replacement within 5 years. The only current treatment method is heart surgery to implement a prosthetic valve, and this will either be a mechanical valve or a biologically created valve. Though they both have their pros and cons, they are considered more to be temporary fixes rather than a cure. By understanding more about CAVD and calcification, we can offer more permanent treatment opportunities in the future. There are 2 major calcification pathways associated with CAVD: osteogenic and dystrophic. While there is plenty of research focused on the osteogenic pathway in CAVD, the information about dystrophic only utilizes 2D cell culture systems, which are inadequate for modeling the 3D environment of the aortic valve. There are both osteogenic and dystrophic 2D calcification models. Though there are positives and negatives, we need to use a 3D model since mechanical stress contributes to dystrophic calcification. Animal models, which are 3D, also have their positives, but are complex and not in a controlled environment. Based on this, we are focusing on creating a 3D dystrophic cell culture model, which brings us to our goal, which is to develop a 3D in vitro model to study the mechanism of dystrophic calcification. To meet our goal, we will approach the problem by creating spheroid aggregates, embedding these aggregates into a hydrogel, and then applying a tensile stress to the hydrogel with the aggregates inside of them. So for our first objective, in order to create our spheroids, we made non-adhesive, ultra-pure agarose microwells. This was achieved by using a PDMS master, in which a sterile melted agarose solution is dispensed and left to solidify for about 10 minutes. The agarose mold can then be carefully removed and put into a culture plate. Afterwards, the microwells can be loaded with a concentrated cell solution of approximately 1 million cells per mold. Spheroids begin to form about after 24 hours, but leaving them for at least 3 days in the microwells ensures that they will form strong aggregates. Then for our second objective, we needed to produce a stretchable hydrogel, and from the literature we concluded that fibrin, collagen, and a co-gel of JAMA and HAMA were worth exploring as possibilities. So we have consistently been making collagen, the JAMA, HAMA, co-gel, and fibrin to see how they react to tensile stress and to see how the aggregates react to being embedded in this environment for 7 days. So in order to embed the aggregates into the gel, we invert the agarose mold that we created into a non-tissue culture coated dish. We then rinse the plate and suspend the aggregates in a media at a given concentration. And then we make the pre-polymer solution gel and mix the aggregate suspension in this, and then we polymerize them through either light or heat. So here you can see the results of embedding aggregates into a collagen gel for 7 days, and we were surprised with this one because it's so similar to fibrin but did not have any cell migration or any sign of suspected cell death. When we embed aggregates into fibrin on day 3, we saw signs of cell migration. After embedding aggregates into the JAMA HAMA co-gel, we saw signs of migration on day 5. So we attempted to stretch the gels in the cell scale simulator for 7 days at 10% strain and are currently in the second trial of the step stretching period. The video above shows the day 1 stretching of collagen. Aggregation can occur after 1 day, but the cells are no longer viable after 9. So we are embedding the aggregates on day 2 after culturing and stretching them for the rest of the 7 days. From here, in order to gather data from all our gels that are being stretched, we spread graphite powder in the gels that do not contain aggregates. The fine powder is sifted onto the gel and creates a pattern that can be used for strain distribution. We then use a macro lens and image the gels once a day for a 7-day period, and from each day, we get at least 10 images. From here, we use PIV on MATLAB to create a strain distribution curve over the course of the 7 days, and the images above you can see the speckle pattern of the collagen gel and the strain rate color map based on the velocity field for day 1 of stretching. Although we only have preliminary data right now, the results that we have obtained so far are promising and show that our model can be developed to better model the stresses experienced by the aortic valves.